In this lecture, we're going to be looking at power amplifiers. So like we usually do, when you have gone through the lecture and you have any doubts, you just leave a comment on the comment section, and then all your doubts will be clarified. Feel free to like, share, and subscribe to the channel. Now, my name is Linus Antonio Oforiajikum. For short, my name is Linus. So with power amplifiers, what we're going to be looking at basically, a power amplifier is a large signal amplifier. Okay, so power amplifiers or large signal amplifiers usually generate both large output currents and voltages. Okay, the input to the amplifier should ideally be a large voltage signal, hence the large signal amplifier, and it's usually taken from the output of a voltage amplifier that is called a pre-amplifier. So normally you would have your signal source, which is this one. Okay, this could be any electronic device that accepts the signal as a signal source. By the way, this block here is just a simple amplifier system, okay, where you have the signal source, you have the preamplifier, then you have the power amplifier, and then you have the load. Okay, so usually what will happen is that you have a signal source that will pick your signal, and this signal is said to be a large signal. Okay, now this signal will usually be taken through a preamplifier, and then the power amplification produced is a product of the voltage amplification and current amplification, and that is usually done at this stage. The main job of a power amplifier is to deliver power, that is power P, which is a product of V and I, okay, to the load. So a simple amplifier system is what is shown here, where you would have your signal go through a preamplifier and then a power amplifier, which would now give us an output of the current times the voltage, or a product of the current and then the voltage, and then that will be given to the load. So basically that is what a power amplifier does. Now let's look at power amplifiers and some basic characteristics of power amplifiers. An amplifier receives a signal, like we initially said, from a source. So when you look at this side, you have the signal source. Okay, it could be some pickup transducer or other input sources, and provides a very large version of the signal. Okay, now that large version of the signal is usually produced to some output device or another amplifier stage. Okay, so the input transducer signal is generally very small and normally would have some millivolts, some very small voltage. Okay, they would usually have voltages which are very small. Okay, all right. In some cases you would have them from a thermocouple input or a few microvolt from an antenna when we're looking at telecom, which needs to be amplified sufficiently to operate an output device. Okay, in small amplifiers or in small signal amplifiers, the main factors are usually amplification, linearity. So when we take small amplifiers, the main factors we'll look at is amplification, linearity, and also magnitude of the gain. Now, let's look at large signal amplifiers on the other hand. Large signal amplifiers. Okay. Since signal voltage and current are very small in small amplifiers, the amount of power handling capacity of these small amplifiers and the power efficiency are not usually of a much concern when it comes to small amplifiers. So very often what we bother ourselves with when it comes to small amplifiers or small signal amplifiers is the amplification linearity and also the magnitude of the gain. Now, for large signal power amplifiers on the other hand, primarily they provide sufficient power to an output load to drive, for instance, a motor or other power devices, typically several watts to hundreds of watts. The main features in this case for large signal amplifiers are the circuit's power efficiency. Okay, so here we have power efficiency. The maximum amount of power that the circuit is capable of handling, that is maximum amount of power, that is maximum power, and then also the level of distortion of the output signal, the level of distortion of the output signal. In fact, one method used to categorize amplifiers, as we earlier on looked at, is by their class. Okay, basically amplifiers or amplifier classes represent the amount the output signal varies over one cycle of operation for a full cycle input signal. We would look at amplifier classes as we move on, but before we do, let's look at one of the major characteristics of large signal amplifiers or power amplifiers, which is the power efficiency. Okay, so now power efficiency is basically the measure of the ability of an active device to convert the DC power of supply into AC power delivered to the load. Okay, so a measure of the ability of an active device to convert its DC power supply into AC and delivered to the load is what we term in most cases as power or conversion. In this case, theoretically, we would look at it as efficiency. Okay, so the efficiency of an amplifier is defined in most cases as the ratio of the output signal power supplied to the load to the total power drawn from the DC power supply. Okay, so in this case, the DC power supply to an amplifier by a DC source would be P DC equals to VCC times ICC. Okay, where our VCC in this case is the DC supply voltage, and then our ICC is the collector current. Mind you, we are still dealing with amplifiers, so transistors are still much of an importance here. Alright, so but mathematically, efficiency, which is normally represented by this symbol, is given as P out P out divided by P in times 100%. Okay, so the P out is the output signal power, and then the PDC is the DC supply. So in some cases you would see this to be P in, or you could also term it as what PDC. Alright, so that is the power efficiency, which is also another characteristics of power amplifiers. Now quickly, we're going to move into the classes or power amplifier classifications, where we would look at the amplifiers in terms of their classes. Now, for the scope of this course, we have the class A amplifier, the class B, the class AB, the class C, and then the class D. But our main concentration is going to be on class A, class B, and then class AB, even though we would look briefly at class C and also would look at class D. So quickly, let's look at what we have here, but just to give you some more insight, on the basis of normally the configuration and the mode of operation, the amplifiers are normally classified, as I have already stated here, into different classes. Classes of power amplifiers include, as you know, the A, B, C, AB, D, E, and so on. This classification is one of the most important for power amplifiers since it reflects the trade-off between efficiency and linearity. Okay, All right. So we quickly move on to the Class A amplifier. So the diagram you see here is basically a Class A amplifier. Okay, so here the simple transistor circuit you see in this diagram is a Class A amplifier. Class A amplifiers are usually biased with a DC voltage applied across the transistor base emitter region, okay, which is this region, the base and then the emitter region, okay. All right, now so that there are no signals operating, okay, or so that they are quiescent, or no signal operating point is on a linear part of the transistor characteristics curve. Now, usually in a Class A biasing, the collector voltage is kept mostly at half the supply voltage, okay, and this allows collector current to flow during the complete 360 or during the complete cycle of the signal, of the input signal, and this will provide an output which is a replica of the input, so that you would have the same signal as the input being delivered to the output. However, this means that the transistor is permanently passing collector current even when no signal is applied, okay. So power is being wasted in this case, and although Class A provides for very low distortion, so one thing you should know here is that for the Class A amplifier, permanently the collector will be passing current, and the one disadvantage of that is that there will be wastage of what? Power. Okay. One good thing is that distortion is very low. Low distortion. However, it is relatively inefficient. Okay, it is inefficient in its use of power. So there is a solution for this, or there is a way of mitigating this, okay. But before then, let's look at the Class A amplifier waveform. So in a Class A amplifier operation, the entire input signal waveform is faithfully delivered, okay, or reproduced at the amplifier's output, as the transistor is perfectly biased within its active region, thereby never reaching either of its cutoff or saturation regions. This then results in the AC input signal being perfectly centered between the amplifier's upper and then lower signal limits, as you can see in this diagram. So it delivers the same input at the output, okay. All right, now the maximum possible overall efficiency of a Class A amplifier with resistive load. So the efficiency with resistive load would be equal to 25%. Okay. However, the maximum possible collector efficiency. Okay, now note this is overall efficiency of the system. So the collector maximum efficiency. In this case is 50%. Okay, but in an instance where an output transformer is used, both the overall resistive load efficiency and the maximum collector efficiency with resistive load is also 50%. Okay, so these are some of the things you should take note of. You should be very mindful of these. Now, one thing that happens with Class A amplifiers is that Class A amplifiers can easily get overheated because of the high power dissipation. You remember we said there is wastage of power. So one of the ways of improving the Class A amplifier is current handling ability, is the use of heat sink. Okay, another way to increase the current handling capacity of the circuit while at the same time obtaining a greater power gain is to replace the single output transistor, which we saw in the previous diagram, with what we call a Darlington transistor. This configuration increases, or this configuration has two transistors, okay, with a single package, and that is what we call the Darlington transistor. Now what happens is that the overall gain value of the Darlington device becomes the product of the two transistors TR1 and then TR2, okay, put together. This gives very high current gains along with high collector currents compared to a single transistor circuit, which would usually leave us with dissipating too much heat. The Darlington transistor configuration comes in to take away that problem and then also give us what? Very high gains along with the collector currents. Okay, so that is the Class A amplifier. Now let's look at the Class B amplifier. We would look at the diagram shortly, but here let's start with the waveform. In this case, the transistor bias and signal amplitude are such that output current flows only during one positive half cycle of the input signal. So at 0 signals, the collector current is 0 and no biasing is required. That is at 0 at this point. Okay. The operating point is selected at collector cutoff voltage because of total absence of negative half cycle from the output signal. So if you would observe from here, there is no output at the negative half cycle of the output signal. Okay, and because signal distortion at this point is very, very high. Now, if you compare this to Class A amplifiers, you would realize that average current is very low. Okay, the average amplifier's average current is less. Power dissipation is also less. So overall efficiency is much better when it comes to Class B amplifiers compared to Class A amplifiers. Theoretically, okay, the efficiency in class B operation is about 78.5%, while it is only 50. So this is for class B, and then for class A, if you recall, or as you would recall, the overall efficiency is 50%. Okay, all right. So basically what we're trying to say here is that for a class B, normally you would have the output only giving us the positive half cycle of the input signal for class B amplifiers. Okay, all right. Now the reality of the matter is that a single class B element is rarely found in practice. Okay, so normally a practical class B circuit, or a practical circuit using class B element, is a complementary pair where you have an NPN and then a PNP, or in some cases it is termed as the push-pull arrangement. Okay, here what happens is that you have an NPN and you have a PNP transistor, okay, in the configuration, and that is normally a practical circuit for a class B amplifier, which in some literature you would see it labeled as the push-pull arrangement. Okay, the complementary devices, or these complementary devices, are used to each amplify the opposite halves of the input, that is the positive and then the negative halves, which is then recombined at the output. Okay, so at the end of the day, you would now get both the positive half cycle and then the negative half cycle. Okay, all right. Now, push-pull amplifiers uses two complementary or matching transistors, as we have already mentioned. One being the NPN type and the other being the PNP type, with both power transistors receiving the same input signal. So the same input signal, okay, to the base, that is equal in magnitude but opposite in phases to each other. Okay, now this results in one transistor only amplifying one half cycle. So one transistor amplifies the positive half cycle, and then another one amplifies the negative half cycle. Okay, so that at the end of the day, the positive and then the negative half cycles are put back together to have them the output. Class AB amplifiers. Class AB amplifiers. Class AB amplifiers. Now, a class AB power amplifier is biased at a DC level above 0. Okay, it's usually biased above 0 current level of the class B power amplifier, and above 1/2 the supply voltage level of a class A amplifier. Now, class AB amplifier operation still needs a push-pull connection to achieve a full output cycle, but the DC bias level is usually closer to 0 base current level for the better efficiency. So for class AB operation, the output signal swing occurs between 180 degrees and 380 degrees. And in this case, it's neither a class A nor a class B operation. Its efficiency, however, the general efficiency is higher than that of the class A. So its general efficiency is higher than that of class A, and we know the class A efficiency to be 50%. So if it is higher, then it means that it is more than 50%, okay? But lower than that of a class B amplifier. And we know the class B amplifier has overall efficiency of 78.5%. So for the class AB, the efficiency is said to be between 50 and 78.5%. Okay, between. Okay, between. So it will be 51 to 78.4%, depending on how you decide to put it. Okay. Now, note that the class B push-pull arrangement is less efficient than a class AB. Okay. All right. So quickly, let's look at the class C amplifier. I am not going so much into detail because the scope of this course is to just introduce you to these classes. Now, in class C, the bias point is placed well below the cutoff, and so the transistor cutoff for most of the cycle of the wave. So for the class C, what we have is that the bias point is placed below cutoff. Okay. Now this gives much improved efficiency to the amplifier, okay, but very heavy distortion. So even though there will be efficiency is very high, but distortion is very heavy. Okay. Now, class C is therefore not suitable for many amplifier application. It is, however, commonly used in high-frequency sine wave oscillators and certain types of RF amplifiers, where the pulses of current produced at the amplifier output can be converted to complete sine wave of a particular frequency by the LCR resonant circuits. So very often you wouldn't see a class C power amplifier being used, okay, because of the issue of high distortion, even though it promises very high efficiency. And then we have the class D power amplifiers. In the class D power amplifiers, the signal, which is mostly audio, is first converted to a digital signal, okay? Sorry. Just a second. Okay, so the input signal is converted to some type of digital, is converted to some digital signal, which in most cases we call the pulse width modulation. Okay, which in most cases we call the pulse width modulation. Because the pulse width modulation, PWM, pulse width modulation. Okay, when such a signal is amplified, very little power is dissipated in the amplifier, and in this case it results mostly in greater efficiency than in analog amplifiers. So for the Class D amplifier, the efficiency is very high. My touch screen is very high. Now normally what happens here is that the conversion is normally done by what we call an analog to digital converter, which would normally convert the input signal from an analog form to a digital form. Okay, when this is done, the signal is amplified, and then very little power is dissipated in the amplifier. Now because this is now a digital form, efficiency is very high than you would find in an analog amplifier. After this amplification is done, the pulse width modulated signal, okay, is finally converted back to an analog form using a digital to analog converter and given to the output. So these are the amplifier classifications we have. These are the amplifier classifications. We have looked at the A, B, C, A, B, and then the D.